matrix shares some similarities with the eigendecomposition of a square matrix, and so we're going to borrow some of those ideas when we construct our singular value decomposition. The eigendecomposition of a symmetric positive definite matrix is S equals PD P transpose. The corresponding singular value decomposition is S equals U sigma V transpose. So if we take U equals P and V equals P and D equals sigma, then we can see that for a symmetric positive definite matrix, the singular value decomposition and the eigendecomposition are essentially the same. Let's take a moment to explore how the singular value decomposition is constructed. Comparing a singular value decomposition of an m by n matrix A is equivalent to finding two sets of orthonormal bases, U and V. From these ordered bases, we construct the matrices U and V. Our plan is to start with constructing an orthonormal set of right singular vectors V1 through Vn. We then construct an orthonormal set of left singular vectors U1 through Um. Thereafter, we'll link the two and require that the orthogonality of Vi is preserved under the transformation of A. We begin with constructing the right singular vectors. The spectral theorem tells us that the eigenvectors of a symmetric matrix form an orthonormal basis, which also means it can be diagonalized. Moreover, we can always construct a symmetric positive definite matrix A transpose A from any rectangular matrix A. Thus, we can always diagonalize A transpose A and form A transpose A equals PD P transpose, where D is a diagonal matrix consisting of eigenvalues. E is an orthogonal matrix here, and it's composed of the orthonormal eigenbasis. We also note that all the lambdas are greater or equal to 0. Now, if we assume for a second that a singular value decomposition of a matrix A exists, then A transpose A would equal the transpose of U sigma V transpose times U sigma V transpose. That's equal to V sigma transpose U transpose times U times sigma times V transpose. U transpose U is the identity matrix, which leaves us with V sigma transpose sigma V transpose, or essentially V times the matrix of sigma squares down the main diagonal times V transpose. So right away, this gives us that the sigma i's squared are equal to the lambdas. Not only do we get that the sigma squares are equal to the lambdas, we also get quite quickly that B transpose has to be the same as P transpose, which means the only thing we need in our A transpose A equation is to find U. But we can find U by solving AV sigma transpose. So there is a little housekeeping when it comes to the size of these matrices, but essentially that gives you a step-by-step process of finding a singular value decomposition. So you begin by finding A transpose A, you find the eigenvalues for A transpose A, then you find the unit eigenvectors for A transpose A. V is the matrix of the unit eigenvectors. Sigma is the diagonal matrix of the sigmas, and that has to be the same dimension as our original matrix A. We compute AV, we normalize the columns of AV, we find U, and then we normalize the columns of U. And those are the steps that we need to follow to get singular value decomposition. Next, we'll walk through a couple of examples. First example, we'll find a singular value decomposition for the matrix A, which is equal to 4, 3, 0, negative 5. Computing A transpose A, we get 4, 0, 3, negative 5 times 4, 3, 0, 5, which is equal to 25, negative 15, negative 15, 25. Computing A transpose A minus lambda I, we get 25 minus lambda, negative 15, negative 15, 25 minus lambda. The determinant of that is lambda squared minus 50 lambda plus 400, which we factor to be lambda minus 10, lambda minus 40. Setting that equal to 0, our lambdas are 40 and 10. We'll start with our largest lambda, 40, which gives us a sigma value of root 40. So our A transpose A minus lambda I in this case is going to be negative 15, negative 15, negative 15, negative 15. Set that equal to the 0 matrix. And that occurs when x is equal to negative y. So we can take the vector negative 1, 1, normalize it to be 1 over root 2, and off we go. When lambda is equal to 10, or sigma equals root 10, our A transpose A minus lambda I is 15, negative 15, negative 15, 15. Set that equal to 0. And we find here that x has to equal y. So we've got 1 over root 2 times the vector 1, 1 when we normalize. So our matrix V is going to be negative 1 over root 2, 1 over root 2, 1 over root 2, and 1 over root 2. Our sigma matrix is root 40, 0, 0, root 10. If A is equal to U sigma V transpose, then U has to equal AV sigma transpose. Keeping this in mind, we find AV. Our matrix A is 4, 3, 0, negative 5. Our V is negative 1 over root 2, 1 over root 2, 1 over root 2, and 1 over root 2. So our AV is negative 4 over root 2, negative 8 over root 2, 4 over root 2, negative 2 over root 2. Next, we need to normalize this. Normalizing the columns, we see that we have to multiply the first column by 1 over root 40, and the second column by 1 over root 10. So this gives us an AV normalized matrix of negative 1 over root 5, negative 2 over root 5, 2 over root 5, negative 1 over root 5. And again, we note that U is equal to this matrix times sigma transpose. So taking the matrix, multiplying it by sigma transpose, which is root 40, 0, 0, root 10, we get negative 2 root 2, negative 4 root 2, 2 root 2, and negative root 2. Next, we normalize the columns of U. The column 1, the first column has length 40, like root 40, so we divide by root 40. Second column has length root 10, so we divide by root 10. This leaves us with a U of negative 1 over root 5, negative 2 over root 5, 2 over root 5, and negative 1 over root 5. And therefore, our A, matrix 4, 3, 0, negative 5, is our matrix U, negative 1 over root 5, negative 2 over root 5, 2 over root 5, negative 1 over root 5, times our matrix sigma, root 40, 0, 0, root 10, times V transpose, negative 1 over root 2, 1 over root 2, 1 over root 2, and 1 over root 2. In our next example, we're going to find a singular value decomposition for matrix A, which is 1, negative 2, 0, 1, 1, 0. Again, we compute A transpose A. In this case, it's 5, negative 2, 1, negative 2, 1, 0, 1, 0, 1. When we look at the characteristic polynomial, we get negative lambda cubed plus 7 lambda squared minus 6 lambda, which factors to lambda times lambda minus 6 times lambda minus 1 equals 0, which gives us 3 eigenvalues, 6, 1, and 0. The 3 eigenvalues give us 3 eigenvectors, 5, negative 2, and 1, 0, 1, and 2, and 1, 2, negative 1. When we normalize these, the first vector gets divided by root 30, the second by root 5, and the third by root 6. So we've got our vector v, 5 over root 30, negative 2 over root 30, 1 over root 30, 0, 1 over root 5, 2 over root 5, 1 over root 6, 2 over root 6, negative 1 over root 6. Our sigma has the square root of our eigenvalues down the main diagonal. Now remember that sigma has to have the same dimension as A, which means sigma is going to be 2 rows, 3 columns. So root 6 and 1 are on the main diagonal, and we're padded with zeros. Next, we compute AV, because recall that U is equal to AV sigma transpose. So AV, as it turns out, is 6 over root 30, negative 12 over root 30, 2 over root 5, 1 over root 5, 0, 0. When we normalize the columns of AV, we end up with 1 over root 5, negative 2 over root 5, 2 over root 5, 1 over root 5, 0, 0. Recalling that U is equal to AV sigma transpose, we get U equals root 6 over root 5, negative 2 root 6 over 5, 2 over root 5, 1 over root 5. All that's left here is to normalize the columns of U. So we divide the first column by root 6, and the second column is already of unit length. So U, in the end, is 1 over root 5, negative 2 over root 5, 2 over root 5, 1 over root 5. So matrix A, 1, negative 2, 0, 1, 1, 0, is equal to the U matrix, 1 over root 5, negative 2 over root 5, 2 over root 5, 1 over root 5, times our sigma matrix, root 6, 0, 0, 1, 0, 0, times V transpose, 5 over root 30, 0, 1 over root 6, negative 2 over 30, 1 over root 5, 2 over root 6, 1 over root 30, 2 over root 5, negative 1 over root 6. In our next video, we'll talk a little bit more about the difference between eigenvalue decomposition and singular value decomposition.